Thank you. Thank you, Radu. It's a privilege to be here today to brief you guys. I'm from MITRE Corporation, and every time I brief this, I get disappointed engineers because people think I have somehow came up with a time machine. So if you think that somehow reversing time, I sincerely apologize for any disappointment today. The other thing with this time reversal, as a mathematician, I've also became an engineer. So I do apologize that I may switch my words between transfer function and Green's function. So I am a bastardized mathematician that way. But thank you for this morning. And I really want to appreciate the FFT folks for inviting me today. So quick thing, what is time reversal? It's something, conceptually, it's very simple, but it has a lot of interesting physical behavior. So one of the things I'll talk about today is just give you a brief introduction, what's actually happening with this time reversal in acoustic and electromagnetic research. And the third bullet there was a work that myself, Margaret Cheney from CSU, and Eric Mokel, used to be at NRL, has done, that there might be some relationship between time reversal and resonances. And this idea of singularity expansion method, which I'll talk more about. And then we'll talk a little bit about motions. When things are moving, how would the time reversal operator bring that features out? So what is time reversal? It's really not that complicated. Imagine you have a function here. This is a quadratic function with a rectangular function. Multiply to it, and what you're doing with time reversal is essentially just switching this around in time. And okay, that's very simple, but why do I care? Just a quick mathematical refresher here. As you know, in the Fourier transform of a function can be defined as that up here, and the way of doing time reversal is simply the complex conjugate of that Fourier transform. And this has interesting features, and in optics, I want to bring this up because it does make a point. In optics, let's say you have a regular mirror that's sitting over here, and a light wave comes through some distortive medium right here. So it's, you know, Snell's law, it's going to do its thing, and it's going to come out, and as it hits that mirror, again, Snell's law come into play. So the incident angle and the reflection angle is going to be the same, and it's going to come out, and the distortive medium does its thing, and then it comes out, and the light ray comes out onto the other side at some angle. But when you have a phase conjugate mirror, so let's say the light wave is coming down, it goes through the distortive medium, and you have this mirror that actually reverses in time. What it will do is you will actually send it back in the way that it came from. And in fact, you will undo this distortive medium and come out exactly the way it came in. So so back in the 50s, a guy named Bruce Bogert at Bell Telephone Lab thought about this and said, hey, why don't I use this method to undo distortions? Because they had a lot of issues with the transmission line, and there were a lot of distortions. And so being an engineer, he calls it network, the transfer function. I like to call it Green's function, but please, the transfer function here, he says, okay, let's see how can I undo this distortion. So what he did was he sent an impulse through, and out of the impulse coming out of that network, you get some response to that pulse. And then in the normal way, he would take the same pulse and then resend this signal back through that network, and then you get this result at the end. Okay, but what happens if I take the response of that, time reverse it, and then send it back to the network? The result is a sinc function at the end. And as you know, a sinc function is analogous to a direct delta. So we love direct delta functions, right? When we convolve direct delta functions with the functions, you get it right back. So he, taking this phenomenology, he said, why don't we do that with the movie screen? And this is exactly what it did. So with no time reversal, he finds that the screen does not do, the image does not do very well. In fact, the network just continuously distorts the picture. But when you do the time reversal, he gets this image back. So this kind of stuff they were already thinking about back in the 50s. But it wasn't until really into the 90s, some researchers by Prada and Fink, so they were thinking about, okay, if I have a bunch of scatterers or targets out there, what is the best way for me to focus acoustic waves onto that target? And they set up this experiment, and basically what they did was they created an acoustic array. And each one of these arrays can record, process, and transmit waveforms. And so what they'll do is they'll start off all together at the same time, and they'll broadcast. And they put 2 point scatterers out there. And one is going to have a stronger reflectivity than the other. So when this wavefront comes out and hits, you get this wave interaction, and it comes back. And so you got one wavefront going this way and another wavefront going that way. And they capture that, they reverse it in time and send it right back. But what they discovered was that this wavefront now, what initially they all started at the same time transmitting the same waveform, has now different types of waveforms for each of these sensors to transmit. And when that goes out, there's a focusing effect. In fact, as the wavefront now leaves, more energy is now focused on A, which is your stronger scatterer. And that scatterer will return it will return the wave fields back. And it will have a different set of waveforms. And if you keep doing this process, what ends up happening is all the energy of the wave field starts focusing onto the stronger scatterer and less so on the weaker scatterer. And ultimately, this waveform converges. This is another experiment that they did in 1995. They transmitted the waveform, and you can see that in the initial return, you can see one going this way and one going this way. They had 2 wires in here, and one was a stronger scatterer than the other. And as they iterate, they get converged to a single wave field there. And if they take this wave field and keep broadcasting, you'll see that all the energy of that wave field will focus on one of the stronger wires. So that same group and his PhD student, Davy here, Fink's PhD student, Davy, said, why don't we try this through the wall? Because the wall is very distortive. It has all kinds of material in there that really, really distorts the wave field. And so they put an array right near the wall, and behind they put 2 targets. And they will capture the return of the wave field through this wall, time reverse it, and send it back. And in fact, they get focusing. So independently to all these experiments, there were a few mathematicians, Margaret Cheney and David Isaacson, and they were trying to solve a problem. And the problem was, what is the waveform that I need to transmit that will give me the strongest return signal for detection? And it was a mathematical exercise. And what they did was they created a half plane so that the differential equation could be solved. And they realized that to get to that single frequency waveform for the best scattered wave can be approached through this power method type of iterative power method type of method. And it turns out that this method is what Prada and Fink were doing through the experiments, this time reversal experiments. Now, Cheney and Isaacson, so Cheney extended that work from the acoustic to the electromagnetics with Gerhard Christensen. And while we were doing this experiment, I mean, while they were doing this, it occurs to me, how does the waves know what's out there, and how does it know where to focus? So and when the wave fields do come back, how does it know the temporal and frequency information to go focus there? And as we were doing this examination, we discovered that the time reversal actually excites the resonance of that target. And it really came arbitrarily. We made a couple of very toy-like problems by putting some point scatterers to see, well, how does the wave know about this? So we put point sources, point targets out there, and we were just playing around. And it turns out that by the act of doing this time reversal, it pulls out resonances. And we'll talk about that here. So what's the model? We started off with a basic Helmholtz equation. K is your wave number, and E right here is a total electric field with some source, J. And that J are the point sources that are out there. The scattering, excuse me, the source out there. And then we model this scattering potential. You know, if there's target out there, you got free space, and if there's a target out there, there's a perturbation of that free space. And that's how we model through this scattering potential. And what we did was we turned these guys into a delta function so we can solve this operator, this differential equation. We did this in free space. And those integral formulation results in the Lemon-Schweiger equation, where you have the Green's function, the scattering potential, and the total field. The scatter field now can be written in terms of those quantities. And we idealized the scatterer in terms of point scatterers with some strength to it. And so we played around with this. And so what happens is, if you were to, by applying the Foldy-Lax method, we were able to discretize this equation, remove the singularities at the scattering centers, and now you have a systems of equations to solve. And what you get is this, the scatter field. If I was to have two observation points, and each one of these have some source that I transmit, a transmit signal, I can model the mapping from the transmit to the receiver end through these operations. And basically, I call the P the propagation operator. So P transpose essentially takes your transmitted signal and maps the fields over to the scatterers. The delta is this operator right here causes the fields to interact with one another. And then the last P will return it back to where your observation points are. And so if you were to take this and do your time reversal for the next iteration, send it out, receive, do the time reversal, send it out, you get something like this. So at the beginning, you receive, you transmit something, and your S is your scattering operator that takes the transmitted field out, cause all the interactions, and send it back to you. And as we discussed, in the frequency domain, the act of doing time reversal is taking the complex conjugate. So the next time I transmit, I take the complex conjugate of that field, and I transmit. And that is just the complex conjugate of S star T0 star. And the next time you receive is just that multiplied by a scattering operator. And you keep going on and on and on. And ultimately, it's S star S that I'm calling this as the time reversal operator. And it has a lot of nice property. So if you were to take L and you break it down into its eigen decomposition, you'll find out that they have very, very nice properties. You know, the eigenvectors are orthogonal. They are positive. They are definite. They line up very well, and you can take now this information. Now, since we're in the frequency domain, each one of these eigenvalues are functions of frequency. And in fact, these what I'll talk about is that the eigenvectors associated to these eigenvalues are related to the targets that are out there. So what did I do? I had 2 point sources over here, and that single scatterer out there. And I picked one frequency and I transmit, and what you see here is a radiation pattern due to those two sources. And they transmit exactly the same time with no corrections in it whatsoever. And it generates a radiation field like this. And you can see that here's the point scatter. It doesn't see it. It doesn't know it's there. But once you get the return and build that L operator, the time reversal operator, and you find out the dominant eigenvector associated with the largest eigenvalue, go into the time domain of that and transmit, what you'll find is that now the wave pattern has changed so that it's now focusing onto that single scatter. Now these are two sources, so these beams are wide. So had I had many more sensors out there, I could have probably had a much tighter focusing. Here is an example of the beam. You can see when I take these eigenvectors and I say, does this work for every frequency out there? So this is at 100 megahertz, and you can kind of see that there's a beam forming. But let me play this movie here real quick. It turns out that if you were to take the eigenvector for that frequency and you just sweep across all the frequency, every eigenvector actually focuses onto this scatterer. I'm sweeping from 100 to 155. So as the frequency goes up, you're going to get more nulls, but you can see there's always a beam at that scatterer. So okay, that's really interesting. So what do we have two scatterers out there? How did the experiments, in the experiments, we know that somehow these wavefronts know that there's something out there, and it knows how to converge to the strongest scatterer. And in fact, in later work, Prada and Fink showed that you can even do selective focusing, using some kind of by determining the eigenvectors for the other eigenvalues. But we were curious about how does it know. And so what I did was I started with an LFM, so linear frequency modulated waveform. It's essentially just a quadratic, and it has some support, some compact support, and call that what I would say the pulse width of that signal. And these are the specification for it. If you're so this is the stuff engineers care. Mathematicians may not care about this stuff too much, but these are the specs: 10 microsecond trip rate, frequency, and bandwidth of 6.3 megahertz. So I broadcasted this out and see what happens. So in the transmitter 1, so we have transmitter 1 and transmitter 2. And under transmitter 1, this is a time domain waveform, and here's the power spectrum of that waveform, the FFT absolute value. And you can see these is the theoretical eigenvalue, what you will get as an eigenvalue as a function of frequency, the most dominant one, that is. And you can see the waveform has the peaks pretty much aligns to these peaks of these eigenvalue as a function of frequency, for both transmitter 1 and transmitter 2. And the waveforms are slightly different. And if I was to iterate this for 10 iteration, you can see that the power is sharpening up at these key frequencies. Why? In fact, if you were to iterate this so much, you will essentially go to a dominant frequency and have a delta function in the frequency domain. That is your sinusoid in the time domain, right? Which goes back to what Cheney and Isaacson and Cheney and Christensen has shown. The most powerful way, the most powerful scattering back is a single frequency waveform. And that's what this is showing here. It turns out, when you do the math, that the distances between these frequency spikes is associated with the distance between, the projected distance between these two scatterers. Very analogous to Bragg's law. So once we have the received waveform, remember we were all working in the frequency domain, and Carl Baum, so I want to introduce this idea of the singularity expansion method. So Carl Baum at the AFRL weapons lab in 1975 made a couple of suggestions. When you broadcast an electric field, and that electric field hits a target, you get the immediate specular reflection coming from the target. But at some time later, when that electric field interacts with the target, it generates currents, all kinds of stuff, and that creates what he calls a late time response. And that late time response has key information about the target. And in this late time response, you're going to have a whole bunch of poles in the received signal. And that's what this is all about. You have an incident field, it hits a target, comes right back, but at some time later, as the field interacts with the target, it has a late time response and sends another electric field out. And he says, well, the specular reflection is not really going to have any poles. But the material, whatever that's interacting with, it's going to have poles associated to it because it's an extended target. It has some kind of resonance features to it. So he said, I can rewrite the backscattered field in terms of the specular reflection and its late time response. And so if you were to take, so if I was to go back here, remember these are all in the frequency domain. All these R's are in the frequency domain. And so if you take that vector, go into the time domain, you will have to integrate across a whole bunch of poles. And when you do that, you get these residues. And what he says is this are very unique to that target. So is he right? So when we take that waveform, and what I did was I put two scatters, and I'm sweeping frequencies from across from 99 to 104. And as you can see, at some frequencies, there's some wave interaction, but when it hits resonance, you get maximum interaction between the two targets. So all this work is for stationary targets, things that are not moving. What happens when you, yes, thank you. Should be almost done here. So all these wave interactions for a stationary target, but what if it's moving? How do you focus, you know? Sure, if I stand here perfectly still, I send some information back to you. Now you know my spatial and temporal information to send the wave back to this spot. But what if I move here and I'm keep moving? You know, I'm always going to be time delayed, right? I focus it on here and he's just moved over here, so I need to get new information to move my wavefront to a new position. So how do I do this? And it turns out, currently I'm writing a paper with Margaret on this. But the idea is you introduce an extra operator in there. And that operator does the correction. I call this the Doppler operator. But here's the idea. Let's suppose you don't do any correction and you just grab the signal and time reverse. Here's T0, here's a single scatter, and you have a beam now formed onto it because you now know the waveforms to transmit. And you just don't do anything, and this guy has just moved over here. So the red is the original position, and the black dot is the position that it's currently at. So it's moving. The eigenvectors, the waveforms that you're transmitting from these two guys don't know he has moved, so he's still focusing in the old spot. And then the next time he updates, he's trying to move the beam over here, but he's already moved here. So there's no focusing going on. But if you were to introduce this Doppler operator in between the iteration process, what happens is you can now predict where he's going, and as he moves, you can see that the beam is following him. And here's a video. You can see that the beam is constantly following this guy. And that's just because of the Doppler operator that we insert in the iteration process. All right, to conclude, it is interesting now. We just dealt with point scatters here, but what if it's an extended target of some sort? Well, that has material interaction. It has its certain resonant features to it, and it also generates these eigenvalues and eigenfunctions. And how well does it, there's a lot of open questions here. How well does it converge to the target? This algorithm is adaptive, and it's actually very fast. 2, 3, 4 iterations, because of the engine behind that is the power method. So, 2, 3, 4 iterations, as long as those eigenvalues are strictly decreasing, you can get to this convergence fairly quickly. That's all I have. Thank you.